Additionally, we need to talk about kernel and range just as vocabulary words. So the kernel is going to be the null space of a transformation. So remember back when we talked about transformations of vectors and matrices, that when we have something like t of x, then that's just a x. And so the kernel of that transformation is the same thing as the null space of A. Okay. Now the range of T is where we are mapping to. So the range of T is a set of all vectors W in which, as you take these A times X's, you end up getting that vector, okay, in your range. Now, it's important to realize that the kernel is going to be a subspace of V, and then you do your transformation here, and your range is going to be a subspace of W. Range being that, right, our outputs, okay, and so like the linear combination of those outputs is a subspace of your W space. So here's just some examples from the textbook. There is some calculus kind of thoughts around here. So let V be the vector space of all real valued functions that are defined from A to B, such that they are differentiable and their derivatives are continuous. Okay, so just normal functions, differentiable on a closed interval, derivatives are continuous on a closed interval. So if W is the vector space C of A, B, of continuous functions on AV, then we're going to define D to be the transformation that takes F to its derivative. So since I know the derivatives are continuous, that's why W is the continuous functions of all continuous functions on that interval from A to B. And then D is going to map differentiable functions F into continuous functions D. Okay, and that's going to be a subspace on W. We might not get all of them, so that's why it's going to end up being a subspace. We know that because of calculus, that derivative function is closed on addition and multiplication. If you add two continuous functions, you get a continuous function. If you multiply a continuous function by a constant, you get a continuous function. So D is what we call a linear transformation. And the kernel of D is all of the constant functions because their derivatives would be 0. So that makes sense. Remember, the kernel is going to need to be whatever takes you to the null space. So the only thing that as you take the derivative of it would get you to 0 is if it's the constant. So the kernel of this set, it has to be the constant functions because the derivatives are 0. And the range is just all continuous functions. Let's look at a second order differential equation. Now I understand differential equations are not a prerequisite of linear algebra, but it's just a second order derivative function that you can set up as a homogeneous equation. In particular, this differential equation models spring motion. So it's going to end up being like a sine or a cosine curve because you're going to set the spring in motion and you're going to maybe like pull it down and then you'll have a weight on a spring. You'll pull it down and then it ends up like oscillating back and forth. Okay, so it's going to end up having a sine or a cosine wave. So the set of solutions is the kernel of linear transformations that map F particularly into this space. So if that is the case, that we need that set to be equal to 0, then our kernel in this case is the sine and cosine combination that gives you that motion. Because when you apply the second derivative and plug in, you get 0. So that's a very interesting example of a kernel, because the transformation in this case is taking the second derivative and plugging it into the solution. When you do that, the solution curves that end up being a constant times the cosine of omega t plus a constant times sine of omega t end up giving you the null space. Okay, they end up giving you that 0 vector when you take the first derivative and the second derivative and plug them in. That's your transformation that you're doing here, and then that ends up giving you 0. So the kernel is this set of functions, because that operation is what gets you your 0 vector.